Good morning, everyone. My name is Travis Collins. I'm an engineer with Analog Devices. I work in the Aerospace and Defense Group, which is a little bit different than where I was last time when I was here at GRCon. Today, I'm going to be talking a little bit about ADI and go into some parts that you probably we don't really talk about at GRCon. We'll start off a little bit about the company, but then kind of get into some more interesting technical things. So just some background on me. I've been using GR for, I don't know, 10 plus years now. Back in my master's days, myself and a colleague of mine are the original authors of like GRDOA, and right now I help maintain GRIO with a number of others. So, any complaints about Pluto or some of the other IO devices, please let me know. We're happy to add more features if you're using some of the I/O blocks now. Now, just a little bit of background on ADI. So ADI is really foundational in the converter space, data converters, microwave, sensor, all kinds of different devices. We've been around since 1965, and excuse me. But our portfolio has pretty heavily grown through just naturally through development, but also through different acquisitions over the years. With companies like Hittite, which really increased our high-frequency business, with Linear Technology, which gave us more ADCs and DACs, and a lot of power components, and more recently with Maxim Integrated, which really gave us a boost to our kind of commercial space as well. So right now we make around 45,000 different SKUs, so lots and lots of parts over many different industries, from like RF to sensors to precision. Audio is a big market for us, and we're all over the world. So we have design centers all over the globe, and we have, which makes, I would say, design reviews really fun. So usually we're in a call with guys from India, from Wilmington in Massachusetts, Limerick, Romania, which is where some of my team works. But it's really a global company. But ADI, I would say we really do two things really well. We do integration, so we'll take a bunch of components and put them into monolithic ASICs or SIPs or MMICs, things like that. Or we add new features and enable different applications. So that's really what I want to just go into a little bit. So if we go back, say, circa 2012, and if you walked into a LTE base station, you would see a radio head that looked like this, where we have this board on the left here, where we have really discrete sections of the radio, where we have a discrete RX1 section, RX2, ORX or observation side, as well as transmitters on the bottom. So this is kind of typical what you would see in 2012, where we have really discrete components put on a single PCB, and this would be your common radio head. Then if we kind of go up just 1 year to 2013, all those components really got smashed into a single 10 by 10 millimeter package. So this is really the birth of like 9361 and a lot of the generation of modern transceivers that we've seen from ADI over the years. So the chip is on the left, which is like a monolithic ASIC that includes most of the circuitry we saw on those PCBs. And in the middle is kind of a diagram of, it's a really simplified diagram of what goes on inside the transceiver. And on the right is a metal layer, which is a really interesting article from Zepto Bars that goes into 9361, some of the details on the chip. Some of the math isn't really right in the article about kind of the business cases behind it, but it's a really interesting read. One thing you'll kind of notice about the die shot here is this kind of like dense portion on the right. Whenever you see that on a chip, this is the digital sections. And if you look at the generations that come after 9361, this gets bigger and bigger and bigger. So at about now, we're like, that's over half of the dies. So we're adding more and more digital into the components that are coming out. But this is a great example of the level of integration that we do. We take like discrete mixers, discrete LNAs, and then smash them into a single ASIC, and you get massive swap advantages by doing that. And by putting things on a single process node, we can get a lot more advantages, control things, get much more performance by doing that, start introducing algorithms into the design, things that you can't really do or are really challenging to do with discretes. So that's part of our integration business. And the second is more adding features into hardware that enables different applications. So I just want to talk a little bit about our beamformers, which is a new area that ADI has been kind of getting into for the last few years. If you're not familiar with beamformers, I'm primarily talking about analog beamformers here. They work, if we look at the diagram on the left, by taking different feeds on transmitters or receivers and applying gain and phase adjustments to them to build beams or gain in certain directions and nulls in other directions. Now, so you do this by having individual controls on the gain and excuse me, phase of those individual channels. Typically, this is done digitally because it's much simpler to do that than to build essentially hardware that does this for you. But having a single ADC, single DAC on every channel can be very expensive and have a lot more power requirements around it. So recently, about 2-3 years ago, we introduced the ADAR1000 beamforming chip, which is this diagram on the right here. Now, how this chip works, it's designed for around 10 gigahertz X-band. We have individual controls, so there are 4 receive paths that come in, which are these kind of red lines here, which will sum together to a single output, or we can have a single feed that goes into the chip, and that will go out to the individual transmitters. And we can individually change their phase and gain to form beams. And this is what the eval board looks like if you want to buy the device today. But how would you really use this in practice? What does a system look like with a ADAR on board? So here's a really good example. We have a kit called the Stingray, which is our X-band development kit. And this comes with everything from the antennas to the ADARs to the up-down converters to get you to 10 gig, as well as the digitizers on the back end. So on the left here, we have just an image of the front end where we have our antennas that are spaced for 10 gig frequency, and they're set up in these kind of quadrants here, where on the back of that antenna face, we'll have the beamformer in red here. And the individual chips that are feeding the antennas are called TR modules. If you're not familiar with TR modules, they're essentially a switch and amplifiers that we use. So each of those panels can, or each of the antennas can operate in transmit or receive mode, and we can control them individually at the ADAR level. Now, you might ask, well, how do I control these things? It's if you're familiar with Pluto or devices from ADI, we provide kernel drivers for them, so we can individually control gain and phase as well as other things. So if you look at the driver today, you'll see lots and lots of attributes that allow you to digitally adjust the phase and gain of each channel, of each ADAR. You can stack multiple of them together and adjust them kind of sequentially together as well. And these chips are a little bit more complex than just phase and gain. There are state machines inside of them, so we can do things like beam sweeps and beam adjustment. We can control amplifiers that sit on the front through bias controls and other state machines that exist inside the device. But again, since this is all driven through I/O at the bottom of the stack, we can just use our traditional GRIO blocks, and we get something like this on the right, and we get individual phases, and we can, as well as gains and other settings, and we can control these beamformers and easily bring up our system and control it as we would expect from a flow graph. So if we kind of look at this holistically, where we have our traditional kind of layout of our system with something like Python or GNU Radio, starting on the right, where we'll have our PC that's attached to a FPGA or similar device, and then our data converter, like a transceiver, high-speed device, something like that. We have more control today where we're extending further out into this microwave domain. And we're adding more and more control into these more traditional kind of like fixed function analog components that you'd see. And the beamformers are a great example of these. So, the Stingray kit that I showed first, that's an interesting device, but it's very, I would say, like purpose-built for one function. We have been working with X Microwave. X Microwave makes this system for RF prototyping. You can think of it as like Lego blocks for RF devices, where you get this grid, the steel grid, stainless steel grid, and you can put down these little tiles and build up your RF system. Now, we worked closely with them to build a daughter board or a bridge board that connects to this kit, so we can individually control these components like beamformers, like mixers, like gain stages, and get them back into our drivers and control them as we would any other device. So, you can think I have a beamformer out front. How do I control that? I have a mixer out front. You hook this up, you get the I/O driver, you use GRIO, and you're good to go. Here's just another example where we're showing off more explicitly this card in red here. So this is kind of a standard kit that you would see from analog devices where we have these FMC cards, which will have data converters or transceivers on them, which are hooked up to a standard kit from Xilinx or Intel that have these FMC connectors. So the additional piece here is that we have a controller board that will bolt up to that X Microwave kit to give you access to these analog parts out front. And we develop drivers so you control them in a single holistic way. From Python, from MATLAB, or GNU Radio. It doesn't really matter. So this is kind of like the final hardware that I'll show, but similar to the big Stingray kit, we have a smaller, more education-focused device called the 80ALM phaser board. This is using the same parts, up converters. It's receive only. It doesn't do transmit from the beamformers. There's an up converter for just a single transmit that comes out. But essentially, it's ADARs on a single board. Then we have a Pi that's mounted on the front for control and data streaming. And then we have the digitizer, which we're just using a Pluto on the back. And this is just a self-contained kit that's great for learning about beamforming, understanding beamforming, and then you can kind of update to or upgrade to the bigger systems when you need more channels, when you don't want to do more, I'd say, unique arrays if you have a different geometry. And ADAR 1000 is really the first generation of beamformers, and we're on the 4000 series now. So depending on the frequency band that you want to operate in, we usually have things that fit into those applications. Now, if you found this interesting, we have lots and lots of openings, ADI, for software people, for HDL people, for hardware folks. We try to do things in a holistic way so that you can have a single consistent environment. Everything is software driven now, software controlled. So it's more adopting the beliefs that we have in software-defined radio and extending that further out to different components into different industries. It's not just radio, it's sensors, it's audio. We're doing things all over the map. And GNU Radio is a great platform for that, and we're building our software and our HDL in a way that cooperates with GNU Radio. But yeah, so as I mentioned, we are in a lot of different industries. So if RF isn't your thing, if you like automotive, if you like 5G or smart systems, digital healthcare, we are doing similar work in these industries. A lot of it is just signal processing at the end of the day. So we use the same tools. It's just you have a different device hanging off the front. So thank you for your time. If you want to learn more about these devices, please come by our booth. We have the phaser, we have the X Microwave kits, and we're glad to talk with you and discuss more about our devices. Thank you very much.